Okay, hello everyone. We have a very special event tonight because we have two very special guests. Our two speakers tonight, Rachael and Jeff, other than being very well-known astronomers, are also the founders of one of the largest astronomy on taps in the country, Astronomy on Tap Austin, Texas, which we modeled this event on. So they really helped us out a lot when we started, and so it's really a pleasure and an honor to have them here speaking at our event today. So Andy's going to tell you the plan for tonight.
Right, so as usual, we will talk. Use his mic. Yeah, I turn it up, you're going to get feedback. Hello, can you hear me now? Okay. So we will start off with the first speaker, that will be Jeff, and then we will have answers to questions to Jeff. You can text your questions to 55AOTSB, and if you have in your cell phone, you can just type those letters, it will come to us. Then we'll have Astronomy in the News, then we'll have a break, and then we'll have Rachael talking about the science of Star Trek, and then we'll have upcoming events, answers to questions, and then a raffle where we give away Astronomy on Tap, the beer glasses, and other awesome stuff.
Yes, and the questions.
That's right. So, and then we answer questions. If you have one of your questions picked, you get a postcard and see people at the front for getting that. Also, there are other things at the front that you can get, like t-shirts and posters and so on.
Yes, and stick around to the end for the beer glass raffle. And we also want to say this is our last event before we go on break, and we're going on break so that we can figure out our funding situation for these events, because we've kind of run out of funding. So we could use your help if you know of anyone or any kind of entity that would sponsor Astronomy on Tap or want to keep this kind of activity going. Please talk to Sandy in the front desk and let her know, even if you're not sure or you think any contact will help us, and we hope to be back in a couple months, newly funded. You can also help us out by getting some stuff at the front desk. We have t-shirts and posters made at our observatory. So these are images you cannot get anywhere else, or at least not by anyone else's, not by from our telescopes. We also have free pens and magnets for you at the front, and today especially we have a few other things we brought in from various conferences, like free bookmarks about gravitational waves that you may have seen when you came in, and we'll tell you a little more about those later, and also a bunch of stuff from the European Space Agency, and that's all free. Just ask for it at the front desk. We'll be happy to give it to you just for coming here tonight. So, I think we're ready to get started.
All right, so our first speaker tonight, Jeff Silverman, who I know well because I study supernovae, and so does Jeff. In fact, my PhD advisor, Craig Wheeler at the University of Texas in Austin, was Jeff's postdoc advisor. And it was there that he founded Astronomy on Tap Austin. And Jeff and I know a whole lot about each other. In fact, so much that I probably didn't say too many incriminating things about him with mutually assured destruction. But I will tell you that he likes to post on Facebook like crazy acronyms about astronomy that are the today's tortured astronomy acronym. I'll give you some examples here. AWSNAP, which is the Australian National University WIFES, which the Wide Field Spectrograph Supernova Program. So now notice that contains two sub-acronyms within the acronym, and random ass letters within the word supernova is not allowed by acronym rules, okay? Now, I do happen to collaborate with some of these people that do that. So they're good people, but it's terrible, terrible behavior.
Maybe we should clarify, Jeff does not make up these acronyms.
No, these are real astronomical acronyms.
No, but yes. And he just, scours papers every day and comes up with these and puts them on his Facebook page for all of us to enjoy.
And another one, holy cow, okay, which has the H0 lenses in cosmograils wellspring. Okay. Now, first of all, the first violation here, H0, that's a 0. That's not an O. Okay. And then cosmograil, that's even an abomination in itself with the first cos part of it and mo part of it and grab part. It doesn't make any sense. And that's just a C and then what is that? An O in this final acronym. And then what the hell is a wellspring? Okay, I'm sorry. That's not a technical term. That's not a technical term. That's just bullshit. And then finally, all sky co-moving recovery of nearby young members. Okay, first of all, what's a member? I don't know. And that stands for acronym. Okay. Meta. Okay. But now I have to say, our co-host here, Yair Akabi, as good of a guy as he is, has contributed to this nonsense. He made an acronym so obscure, I had to look it up on a webpage called Dumb or Overly Forced Astronomical Acronym Site, or DOOFUS. I'm not making that up. That is legit. Okay? Go look it up. And you have to scroll down to the W's here, and there's one that's called Weizmann Institute of Science Experimental Astrophysics Spectroscopy Program, or WITAS. Okay. Which they eventually changed to WISE Rep because the Astrophysical Journal said that is too much ass for our journal. Okay. So,
I don't know what's wrong with it. It doesn't violate any rules. It's all first letters. I think it's perfect. That's my contribution.
All right, but back to Jeff's science. He does amazing research on supernovae. But actually now he's at a startup called Samba TV because he got addicted to the Bay Area, I guess, and stayed up there and wants to make a whole lot of money. But we, of course, if you know us, know a little bit about the backstory of each of these people. And he has visited Disneyland over 600 times. Okay? Who would do that? And in fact, he has changed the course of Disneyland history because he was in the Toontown, him and his family were in the Toontown area where they're setting off with the fireworks. They set them off right behind that. And they, the wind changed or whatever, and the fireworks flew onto him and his family, and in fact even melted his precious parachute pants, which you can see right here. And he took it to the Disney powers that be and got like free dinner and a lot of comp stuff or whatever. But so he knows a whole bunch about cool Disney stuff. In fact, he's on his way to the Disney 2-3 big fan celebration right now. But he is both an awesome scientist and just an all-around cool guy. So here is Jeff Silverman. Yeah.
Thank you guys for that awesome intro. It's a classic Disney story. So the end of that is they now close Toontown and they shoot off the fireworks because my family got burned and got a bunch of free stuff from Disney. All right, so on to what I spent many years doing astronomy research on, exploding stars, dark energy, and the runaway universe. So here's a picture of a galaxy, similar to our own Milky Way galaxy. We can't take pictures like this of our own Milky Way. We don't have a long enough selfie stick. We can't get out of the galaxy and look back. But we think this is basically what our galaxy looks like. It's got a big bulge of stars in the center. There's a supermassive black hole in the center of the galaxy, way smaller than a single pixel in this image. And it's got these dark and bright kind of curvy spiral arms. This one's kind of tilted on its side. We'll see some ones later where you can really see those spiral arms better. But what we have down in this bottom left corner here is a single star in that galaxy that has exploded as a supernova. So one star has exploded at the end of its life and has become about as bright as about 100 billion stars in the core of that galaxy. So these stellar explosions, these supernova, are the violent, powerful death of a star. They can become 100 billion times the brightness of the sun. They can produce enough iron to make 5,000 Earths. The material that's being blasted away is moving something like 10% the speed of light, which is the fastest speed in the universe. So these are hugely powerful, hugely energetic explosions. So a little bit of the history of supernova research. This character figures into the history. Fritz Zwicky, a Swiss astronomer. Most of his career was spent down at Caltech. As you might imagine from this picture, kind of a curmudgeonly old fellow. One of the famous quotes that is attributed to him, he used to call people spherical bastards because they were bastards any way you looked at them. But apparently he was very nice and kind and great to grad students. He really only picked on sort of, people in power, which I appreciate, so that's pretty cool. But he was one of the first guys to really do a lot of the initial supernova science, looking for exploding stars in a very systematic way. He was the one that coined the term supernova back in the 1920s. And so before this, new stars would occasionally pop up in the night sky. The ancients saw this, people throughout history saw a new star in the night sky occasionally, and they would call them nova, Latin for new, a new star, and then they would disappear over time. And so supernova, sort of in the 20s and 30s, astronomers realized it's a bigger cousin of more classical nova, weaker explosions. So I'm going to talk about supernova, the biggest stellar explosions out there. So here is a famous picture that I'm sure many of you recognize. This is the Crab Nebula in the constellation of Taurus. And so this is what's called a supernova remnant. This is what's left over after a star explodes. So a star explodes, it blows out its material, speeding away from it at maybe 10% the speed of light. And eventually that gas and dust that explodes outward from the supernova will just kind of ram into gas and dust floating between stars, minding its own business. So you have this very powerful, fast collision, it heats up, it starts glowing, and you get a supernova remnant. So we see remnants in our own galaxy, maybe some of the nearest galaxies, but I'm mostly going to talk about the supernova explosion itself. And we see these in galaxies outside of our own, much further away. A note about the Crab supernova remnant, I said this is a remnant of a supernova that went off. So this supernova went off in the year 1054. So this is about 1,000 years or so. This picture was taken by the Hubble Space Telescope about a decade ago, maybe 2 decades. And so this is about a 1,000-year-old supernova, give or take. And this supernova that went off in 1054, basically every ancient culture at that time in the Northern Hemisphere noted it. They saw this bright new star. It was bright enough to cast shadows at night. It was bright enough to be visible during the day for about a year, and visible at night for, visible during the day for about a month, and visible at night for about a year. Well before the invention of the telescope. And so there's historical records of this Crab supernova, as it's known, the supernova from 1054. This is possibly one of those observations. It's not quite clear, but this might be. This is from the Anasazi tribe in New Mexico, Chaco Canyon. And we see the crescent moon when they first saw this new star, possibly the picture of the supernova to the left, and then above the artist putting their hand there sort of to give us a scale here. So perhaps this was somebody's PhD thesis in 1054. All right, so here's a series of images of a spiral galaxy, again, like our own Milky Way, but from an amateur astronomer, so a small backyard telescope in a dark sky, not quite as pretty as that first image which came from the Hubble Space Telescope, but same idea. We have a core of stars in the middle, we have some spiral arms kind of on the side. This one's really tilted, so you can't really see the spiral very well. But this is a time lapse. This time lapse is about 3 months long, and this is pretty typical for a supernova. They tend to get brighter for maybe 2 to 3 weeks. They are at their brightest for a bit, and then they fade away over the span of maybe 2, 3, 4 months, something like that. Some supernova are very close by or very, very bright, and we can track them for much longer. People in this room, including myself, have studied supernovae that are 10, 20, 30 years old. But typically, we study them for about a few months, and then they kind of fade away. We don't see them anymore. Another thing that we can do, and this has only been done a handful of times, and this is a really cool trick, is you can kind of zoom in on pieces of other galaxies. So here's a zoom in using one of the biggest telescopes in the world down in Chile on a nearby galaxy. So zoomed in, you actually see individual stars. You see blue-white ones that are very hot. You see reddish ones that are very cold. And you see sort of yellowish, orangish ones like our sun. Those are sort of in between temperature. And so before the supernova went off in this galaxy, in 2005, astronomers took this picture. A supernova goes off in 2008 in this galaxy, in this area. And then a few years later, astronomers come back, they take another picture of this neighborhood, and lo and behold, that star is gone. So one more time, there's a bunch of stars here. 2008, a supernova goes off. 2010, astronomers go back. That star has exploded as a supernova. It's now gone. Now, where those crosshairs are, there's probably a tiny supernova remnant, kind of like the Crab Nebula, but it's way too faint. We're never going to see it in this other galaxy. But to take this kind of picture, you have to be pretty damn lucky. This is what, maybe a dozen stars. Galaxies have hundreds of billions of stars. So you want to measure, very, very precisely where these stars are. You want to zoom in on these galaxies and look at every spot and hope that one of those spots you looked at has a supernova go off, then go back afterwards and see that the star disappeared. So it's a tough deal. Out of the tens of thousands of supernovae people have discovered, this has only been done maybe a dozen times. So very cool. I love that set of images. It's actually from a competing group in Europe that was competing with my old group back at Berkeley, but this set of images I just love showing, so props to them. All right, so back to this lovely picture from the Hubble Space Telescope of the supernova from 1994. So why should we care about supernovae? What's interesting about them? Well, one thing is these physical conditions, the energetics, how fast the stuff is moving, how much energy, how hot it is, we can't recreate in the labs on Earth. So if we want to learn about these high energy explosions and what's going on in the end of the star's life, we have to look at the supernova. We can't do it in a lab, basically. Another thing that's cool about these supernovae is I said they explode outward, this material's moving really fast, it slams into gas and dust that's kind of minding its own business. It can heat up, it makes those cool remnants, but it also kind of jostles that material. And that material might kind of start collapsing on itself under its own gravity once you jostle it. And that's how we have new stars forming. So you have the death of one star leading directly to the birth of new stars, very circle of life. And part of my Disney love, I like bringing that up. Another thing about these supernovae, and one of the things that I found just the awesomest about these things when I was studying them for a long time, was that most of the elements on the periodic table come from stars and these supernovae. So the oxygen we breathe, the calcium in our bones, the iron in our blood, that was all built up in stars billions of years ago and was blasted outward in a supernova and then eventually incorporated into the sun and the earth and us. So Carl Sagan used to say, we're all made of star stuff. And it's very hippie, and I spent time in Berkeley and very kumbaya. But it's literally scientifically true. We would not be here, the chairs you're sitting on, the pieces that make us up, would not be here with a star going through its life cycle, exploding outward, making these elements, and then being incorporated into the sun and the earth, and then us. All right, so what about some stars nearby that we should be concerned about that might go supernova? Okay, just real quick. Okay, so the first one, Betelgeuse. In Orion the Hunter, we see Orion's belt here in the middle. That's pretty obvious even from downtown Santa Barbara, no problem. And then above that, you see this bright reddish-orange star, Betelgeuse, also one of my favorite movies, obviously. So this is a very big star. On the left, you see that this is a puffed up, what we call a red supergiant. So you plop it down in the middle of the solar system where the sun is, it immediately swallows the first few planets. That's how big and puffed up it is. And so this is a type of star that will go supernova. It will collapse on itself and explode as a supernova. And that will happen at some point between tomorrow and 10,000 years from now. That's about as accurate as we can do. People are studying this thing in detail because it's such a nearby, big, close object that's going to go supernova. But that's sort of still the best idea that we have is in the next few-ish thousand years, it's going to explode as a supernova. All right, so should we be concerned? Is this going to, burn the atmosphere and boil the oceans and melt your face like the dudes in Raiders of the Lost Ark? No. We're going to be fine. Don't worry. It will be visible during the day. It will cast shadows at night. It will kind of make your eyes water if you stare at it for a little bit, but it's not going to harm us. We'll be okay. Another star that's interesting and will go supernova and will be perhaps a little bit scarier, but not too bad, is this thing called Eta Carinae. So Eta is a Greek letter. Carinae just means it's in the southern constellation of Carina. So we can't see that from California, but it's a pretty bright star. It was known to the ancients. And then in the 1840s, it suddenly got really bright, weirdly enough, kind of out of nowhere. Not supernova bright, but it got noticeably bright. Stayed that way for about a decade and then kind of gurgled back down to its normal ancient levels. And so, astronomers didn't really know how to explain that for a long time. Some theories were coming out in the 20th century, and then sort of towards the end of the century, into the 80s and 90s or so, astronomers got these pictures from Hubble Space Telescope and sort of had this idea of, well, maybe this thing is an even bigger star than Betelgeuse. This is maybe 100 or 200 times the mass of the sun. Betelgeuse is maybe 10 or 15 times the mass of the sun. So this is an even bigger star. It's going to become an even bigger supernova, but it's also going through even bigger death gurgles. Betelgeuse is kind of burbling around as it's getting ready to die. This thing is burbling around and has these ridiculously huge outbursts. So in 1843, when it got really bright for about a decade or so, it actually burped off those two lobes, the sort of peanut shape that you see. And so those lobes that got burped off are about 10 times the mass of the sun, just in that burp off. So it's been doing these death gurgles since then. And in fact, the lighter pinkish red stuff on the outside was probably a similar eruption maybe 20,000 years ago. So this very big star has been going through these death gurgles and death burps for about 20,000 years at least. And again, it's going to go supernova. It's going to be very energetic. It's going to explode somewhere between tomorrow and like 10,000 years from now. So we can't be much more specific than that. These are very rare stars that are this big. But this is one of them, and it's pretty impressive. Okay, so the real question, should we be concerned? It's going to be much more energetic than Betelgeuse when it explodes. Luckily, it's much further away. So it actually is going to be similar to Betelgeuse. You'll see it during the day, it'll cast shadows at night. It might have some more high energy radiation. You might want to put your satellites in low power mode. If we have moon bases or people in space, they might want to get into their extra shielded area. You might have a Fantastic Four kind of origin story issue, perhaps. But again, not going to boil the oceans, not going to melt your face, so we'll be all right. Okay, getting down into a little bit of the observations and stuff that I've worked on, and many people at LCO and UCSB have worked on as well. So first off, how do we find these supernovae? The ancients, they didn't have internet and TV, they just stared at the sky. They would definitely notice a new star if it popped up. Well, we can do a little bit better than that these days. We can use telescopes like this one. So this is the Rachael telescope out at McDonald Observatory. And this, along with a handful of other ones around the world, are just kind of constantly looking for new supernovae. We think that about 10 supernovae go off somewhere in the universe every second. So in that pause, 10 stars somewhere in the universe have exploded. Most of them are way too faint, way too far away. We're never going to see them. We're never going to observe them. But sort of in the last 15 or so years, we're at the point now where we're finding maybe 10 or even 100 supernovae from Earth every night. So that's pretty cool. And so this is one of these robotic telescopes that does this kind of search. It's robotic and automated. Nobody goes to it, nobody controls it, nobody looks at it. It has weather sensors. When it's dark out and clear, it opens up. It starts taking digital pictures of galaxies, just like from your camera phone. Then compares those to old pictures of the same galaxy and tries to find a new bright spot. Maybe that new bright spot is a supernova. So here's a pair of pictures. The left is no supernova. The right has a supernova. So this is a pretty bright galaxy, nice spiral structure, as I promised. There's a lot of spots to check in both of them, but I will admit that the supernova on the right-hand side is pretty bright. So in some sense, it's easy because it's bright, but there's a lot of spots to check. So it might be tough. I see a couple people pointing, so that's always my cue to point it out to them. I will point out, this was a supernova found in the summer of 2011, and the image on the right with the supernova was taken right nearby, actually. I use this in all of my supernova talks, and just this afternoon remembered that this was taken using some of the Las Cumbres Observatory telescope. So very cool local connection to that slide. Okay, so this is an astronomy talk. I am a data scientist. I'm still a scientist. I'm going to show you a graph. All right. So, wow, people applauding graphs. Damn it. That's a nerdy crowd. I like it. I'll drink to that. All right. So what we have here is one of the typical observations of a supernova. This is what's called a light curve. It's just the brightness of the supernova plotted against time. So the different colors are different filters that we put in the telescope. But the basic idea is we have the supernova get bright for a couple of weeks and then fade away over the span of a few months, just like I showed in that time lapse from the amateur astronomer earlier in the day. So these light curves can tell us actually quite a bit. It can tell us the distance, the temperature, perhaps something about some of the elements in there. Quite a bit of information can come out of these light curves. And so this is what a lot of telescopes do. This is a lot of what the Las Cumbres telescopes do, actually. But that wasn't really my specialty when I was working on this stuff. My specialty was staying up late and listening to classic rock. It was also breaking up the light from supernova using a prism into its component rainbow colors. So this is what we call spectroscopy. We make a spectrum out of the supernova light. If anybody's seen a rainbow, congratulations, you're a spectroscopist. That's what the water is doing to the sunlight. It's breaking it up into its component colors. So what we can do is we can plot the brightness of the supernova light at all of these colors, or in scientist astronomer speak, wavelength. And so there I've got the actual rainbow, the colors of light that we would see. These spectra, as they're called, the brightness versus wavelength, goes a little bit bluer than blue, or more violet, so ultraviolet, and a bit redder than red, so infrared. But sort of centered on the optical visible light we see, the rainbow. And what's cool about this is sort of since the mid-1800s, scientists knew that every element on the periodic table had a very specific spectrum. There were some wavelengths, some colors, where they were very bright. So you can sort of use those as fingerprints and say, okay, well if I see all of these bright lines or bright features, that's this element or that element. And so we can look at a spectrum. These are two different spectra of two different supernovae. And we can look at these bumps and wiggles, and that is totally a technical term that we use. We look at the bumps and wiggles, and I can associate all the bumps and wiggles with elements on the periodic table. So the one in the top left has this big H alpha, hydrogen, this very strong red line of hydrogen. On the right-hand side, we've got a lot of calcium and some of the silicon. Again, this is where these elements are cooked up in the universe naturally. So this is what I did. I did thousands of observations and looked at many of these kinds of spectra. All right, enough plots. Let's go to some vacation photos. How about that? So these are the two twin Keck telescopes on the Big Island of Hawaii, on the dormant volcano Mauna Kea, about 14,000 feet above sea level. These are telescopes that are used for all kinds of astronomy. I got to use these quite a bit for supernova research. These are 30-foot diameter telescopes. So when astronomers talk about a telescope, they talk about the diameter of the biggest mirror or lens. So this one is about 30 feet across. You can't see them, they're sort of in the base of these big domes, but you might be able to make out, I know this laser pointer doesn't work real great, but we'll try. Right there, that's a full-size SUV. So these are two of the biggest optical telescopes in the world. They're very impressive, fun to go to. I did get to go up to the summit one time. There's me a few years back wearing my official Keck ski jacket. I'll point out this was August on the Big Island of Hawaii. So that morning I was on the beach in flip-flops and board shorts at Kona, and then you go up 14,000 feet. Even in August in Hawaii, it gets pretty damn cold, so I'm in jeans and a ski jacket. Another famous telescope that does lots of different astronomy, but has been specifically used for supernova for many years, is of course the famous Hubble Space Telescope. So unfortunately, there's no car next to it. I don't have a picture of myself in front of this one. But I do like to remind people that this thing is about the size of a school bus. So this is pretty big. And so this was used to find sort of even fainter supernova. And so the idea was, ROTC and these smaller telescopes could find supernova in the nearby galaxies, a mere 10 or 100 million light years away. But what if I want to find billion light year away supernova, the furthest supernova that we can see currently? Well, I got to use Hubble in space, or some of the biggest telescopes on the ground in Hawaii and Chile. And so that's what astronomers started to do in the late 90s. So here's one of the Hubble found supernovae, and followed up by stuff on the ground as well, from the middle of 1997. Same idea. You take pictures of galaxies with Hubble or the biggest telescopes on the ground. You come back a few weeks later, you take another picture, you see if there's a new bright spot. And so in May, there's a new bright spot. You can subtract the images from the beginning and end of April, and you see a new bright spot. Maybe that's a supernova. It is, and it's one of the furthest supernova ever observed. This one was about a billion light years away. The current record holder, or at least the current record holder as of a couple of years ago, was about 10 billion light years away. People are still pushing the envelope of that, and that will change quite a bit in the near future. But why were astronomers looking for this? What they wanted to do with the furthest away supernova was they wanted to figure out if they could use them to measure the size and the expansion of the universe. So this is a little bit weird, so we're going to take just a quick little detour here before I get into this last punchline. So the Hubble expansion. So here's a picture of Edwin Hubble at the telescope, namesake of the Hubble Space Telescope, of course. You can tell this is the good old days because he got to smoke his pipe while observing. They don't like that anymore, unfortunately. But Hubble and others in the 1920s realized that the universe is expanding. All galaxies are moving away from each other. And so all galaxies have mass. They have stars, they have dust, they have stuff in them. And Newton, hundreds of years ago, said if you have stuff, you should be pulling on each other through the force of gravity. So you have galaxies moving away from each other. They're all pulling through the force of gravity. And so the logical conclusion is all this pulling should slow down that expansion. All the mutual pulling from all the gravity, all the force, all the material should slow down the expansion. And so these faraway supernovae were being used to measure that expansion and try and measure the slowdown of this expansion. And so the weird thing that happened, and many of you in this room know the punchline here, is that when astronomers tried to measure the slowdown, they found the exact opposite effect. They found that the expansion of the universe was speeding up with time. It was accelerating. So something was pushing galaxies away from each other faster and faster, stronger than the force of gravity. This is weird. This is not what you expect. This is you throw the laser pointer in the air and it zooms through the roof. That's not what you think should happen. So, two separate teams using separate data, separate analysis tools, both published around the same time, the same result. So the supernova community was like, yeah, these guys know what they're doing, that's very interesting, cool, nobody expected that. Rest of the astronomy community was a little more skeptical. What are the supernova guys smoking? That's a little weird. But over the years, other lines of evidence not having to do with supernova confirmed this fact, that there is this something in the universe pushing against gravity, making the expansion go faster and faster every day. And this is what we've now termed dark energy. So eventually, in 2011, about 14 years after this discovery was first announced, these three fellows won the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae. I've worked with all three of these guys. They're all interesting characters in their own right. I love pointing out that Brian Schmidt in the middle there owns a winery down in Australia and has his grad students and postdocs pick his grapes. I've always wanted to do that. I'd love to go down and visit and pick those grapes. I've tried the wine. I'm not a big, huge wine snob, but I could tell some vintages weren't great and some were pretty good. So, but that's one of his crazy hobbies. Okay, so what do we know about dark energy? The stuff was found in like 97, 98 or so. It's now 20 years later. What the hell do we know about it? The answer is not a lot. It's there. Astronomers agree on that. There's something pushing against gravity, pushing the galaxies faster and faster away from each other. We sort of know about how much of it is there, but beyond that, we don't really know what's causing it, why it's there, where it came from, how it'll evolve into the future. So one thing that we do know, I said, is how much of it is there. So this is sort of the basic composition of the universe. These numbers we can quibble about. I'm sure astronomers in the audience have their favorite numbers for all these things, but this is one of the versions. But you can see dark energy makes up sort of over 2/3 of the universe. Almost the rest of it is this dark matter stuff. The only thing that relates those two types of stuff in the universe is the word dark, which, pro tip, if an astronomer calls something dark, it means they don't know what the fuck it is. So dark energy and dark matter make up most of the universe, isn't that funny? Dark matter is a whole other talk involving galaxies and stars within them. Dark energy is what we're talking about here, looking at observations of distant supernovae. Then we got about 4% is intergalactic gas. This is kind of hydrogen between galaxies. And then we got about 1% in stars, planets, and other stuff. And of course, the other stuff involving Earth, you, me, puppies, and beer is a tiny, tiny fraction of that 1%. So at this point, you might be thinking, we're this tiny fraction. You've made me feel really bad. I'm going to go buy a lot more from the bar. Okay. But my old advisor at Berkeley, Professor Alex Filippenko, always likes to, at this point, say, but as far as we know of this pie chart, we're the only slice that can sit here and stand here and talk about this and think about this. So maybe that makes you feel a little bit better. All right, that is all I've got. Thank you guys very much.
Thank you very much, Jeff. We're now going to take a short break. In the meantime, you can stretch your legs, get some stuff in the back, get some drinks, and text your questions for Jeff to this number, 805-55-AOPSB. It will be on the screens. We'll be back in 5 minutes.
Jeff, first question. What happened to the parachute pants, and will you ship them to this person?
So that particular pair that I wore the infamous night in Toontown had multiple burn holes in it. So those, I believe, we threw out. Luckily, at the time, in 97, 95, I think about 95, I had like 7 more pairs of the parachute pants. I think those are long gone, unfortunately. One of the many things I got rid of at some point, like along with my Dare t-shirt and my Ninja Turtle t-shirt. Would have been so cool and like retro now, I know.
Okay, next question. What is so special about supernova measurements that allow them to measure the expansion of the universe?
That's a great question. If I had my hour-long version, I would have gotten into it more. But the quick answer is a certain type of supernova tends to basically be the same intrinsic brightness, the same energy. So it's like a 100-watt light bulb. So if I put a 100-watt light bulb right in front of your face, it's really, really bright. If I take a 100-watt light bulb and I bring it all the way down to downtown LA, you're probably not going to see it, or if you do, it's going to be really, really faint. But what you can do is you can calculate how bright it appears to you, and you know it's 100 watts. You know the amount of energy coming out of it intrinsically. And then you can pretty straightforward calculate the distance to that light bulb. And that's basically what we're doing. A certain type of supernova called the type 1A has an intrinsic energy, intrinsic brightness that's pretty constant. So how faint it appears to us, we can measure the distance. So we use these over the years as sort of distance indicators, or cosmic yardsticks, sometimes they're called. Cosmic standard candles also is another term. Anyway, so we can measure distances to these things pretty accurately. We can measure the distance in a couple of different ways and compare them. And basically what they found in the late 90s was that these specific kinds of supernova were a bit fainter than we expected. And the only way to make that consistent with all the other observations and knowledge of the universe was that this expansion was actually going faster and faster, and these two things were pushed further away than we expected. That's basically how we got there.
All right, next question. So say we could measure the parameters of certain things in many decimal places, but you're saying that there's like most of the universe is unknown. How do you reconcile both of those things?
That's a really deep question. I've never gotten anything like that before. So I guess one way to think about it is there are certain things, certain numbers, certain constants, the value of certain stuff that we can measure very, very precisely. Masses of things on Earth, or timing with atomic clocks. You can have a ton of decimal places after the number of seconds. But that's just sort of intrinsic to the object you're measuring, intrinsic to the numbers involved, and your measurement technique. For supernova or for dark energy, we have kind of big uncertainty. We've only measured a handful of these very far away supernova. We don't really have a theory about where this dark energy is coming from, and so we just we're not as accurate about it. And a large chunk of the universe is made up of that stuff. Of the 1% of stars and galaxies and puppies and beer, we know a lot, and we have a lot of measurements that are very precise with lots of decimal place numbers after the decimal place. So I guess that's my best answer.
All right.
That's a good question, man. That's hard.
Exactly. Are there any crazy other elements we've seen in supernova remnants?
Interesting question. So in supernovae and supernova remnants, we've basically seen elements on the periodic table, stuff that you've heard of. The bulk of stuff that I observed in supernovae were things you've probably heard of: hydrogen, helium, silicon, oxygen, calcium, iron, magnesium, sulfur. Not totally bizarre. Occasionally you might see scandium or vanadium. A little bit weird, maybe we're not as familiar with those, but they're on the periodic table. Astronomers, chemists, scientists have known about these for a while. So we've never really discovered any new element from supernova observations. I will point out, just a quick historical aside, that helium, however, was first discovered from looking at observations of the sun. So that was an element on the periodic table that was actually found in astronomy and space before ours. So that's where you might get that, but not super. Cool question.
Does the proportion of what the universe is composed of mean we are all 1%ers?
That's a good line, and I'm going to steal that.
Also, people have heard that elements up to, I'm going to change the question, but up to iron are made in stars and so on, and then some other elements are made in the merger of neutron stars, and maybe others are made in supernovae. What's the deal with all that?
All right, so the deal with all that, again, in the extended, director's cut of this talk, you'll find out more. But the quick version is, yeah, I sort of talked about oxygen and calcium and iron being cooked up inside stars. That's where most of that comes from. It'd be trapped in the star without a supernova, but the supernova can explode it out and get into the sun and Earth and us. Stuff further than iron on the periodic table, things like copper, gold, uranium, that's really mostly built up in the explosion itself. There's extra energy, and you can make those even heavier elements in the supernova explosion itself. Other things like mergers of neutron stars or winds in massive stars can also make certain elements on the periodic table. I'm less familiar with which ones. Some of those are theory dependent, so it depends which astronomer with a star you talk to in the room. But all the periodic table elements can be made up from a lot of those different aspects. Many of them are from the middle of the star, many of them are from supernovae.
So we have many, many amazing questions, and if you don't get your question asked right here, feel free to stick around or talk to somebody with a glowing star. They're an astronomer, they may know the answer. But one last question, what's the deal with your shirt?
All right, so I've got backup slides because I had a feeling, I'll just press the button. Because I had a feeling people would ask me about this. So first of all, the image is of a cluster of galaxies that was observed with the Hubble Space Telescope. Dr. Rachael, who'll be going on next, is an expert on this field, so you should ask her more about it. But she designed and sewed the shirt, and then we had this idea to kind of trick it out a little bit more, so I'll turn it on, and then I'll explain what the hell's going on. So it'll light up as I'm talking. So what this is showing off is sort of a merger of the research that I used to do and that Rachael currently does. So Einstein, his theory of general relativity, there we go, says that space and that matter can bend light. It bends space and it bends light. So if we have light from a galaxy coming to Hubble, it goes straight to us. If it passes through a galaxy cluster, some of the light will be bent. So it bends light, it curves it, You see some of the light rays that used to pass the telescope now go in it, so things get brighter, they get magnified. And so this is
face the audience here.
We gotta see your shirt.
all right. We'll continue to try and stand this way. So this is basically what a lens does. A lens focuses light, it magnifies, it makes things brighter, it curves things. And so gravity can do this, and that's why we have gravitational lenses. This is Dr. Rachel's expertise. Where this comes into supernova is, so the cluster of galaxies that I'm wearing, it was discovered in 2014. A good friend of mine at UC Berkeley named Dr. Pat Kelly discovered that there was these 4 bright spots around this one galaxy. And deeper observations showed that it's the same supernova. There are 4 images of the supernova. So you'll see that pop up right about here, so every once in a while. So 4 images of that same supernova. And it's not 4 supernovas, it's not 4 stars, it's one star that explodes as a supernova that's getting lensed and bent 4 different spots around that galaxy. And so there's actually multiple images of this galaxy. There's one up here and one in here. And you can see them on there as well. And so modelers and observers and theorists all put their heads together and said, okay, well, we saw those 4 in 2014. We think there was probably one in this way up here galaxy near my boob up here back in like the mid-90s, but we didn't see that. Okay, bummer. But there's supposed to be another one in 2015. And so lo and behold, a year after that first quadruplet of supernovae went off in this galaxy, they did in fact find the supernova. So they predicted it was going to show up in this other image, another path that the light got bent around to, and lo and behold, they found it. So there's actually 6 images of the same supernova in this cluster, one from the mid-90s, 4 in 2014, 1 in 2015. And so Dr. Rachel did some sewing. She has a skirt version of this. I have the shirt version. And we put this all together, so it's actually scaled in time and brightness accurately. So that's why there's a big gap between the mid-90s, 2014, and 2015. And so, yeah.
All right. More than you've ever seen.
Thank you, Jeff. All right, I think we're going to go right into astronomy in the news.
Yes, and we'd just like to remind you, if your question was chosen, you get to see Sandy in the back and ask her for a nice postcard. We have some new postcards as well of different space stuff that you can get. Okay, so astronomy in the news. There's been a few news stories in astronomy this past month, and some of them were reported well and some not so much. So we're going to fix that here. Our first story involves gravitational waves. We've been having gravitational waves almost every month now because it's becoming a big thing. So another acronym in astronomy, LIGO, the Laser Interferometer Gravitational Wave Observatory, has been detecting gravitational waves for a few years, predicted by Einstein 100 years ago, and we've just started detecting them a few years ago from merging black holes. And the way they do it is by having 2 of these systems, which are few mile-long tubes with lasers running through them. And if you were here at the first Astronomy Untapped, we actually did a demonstration of that on stage. We won't go into the details now, so it's lasers crossing a few miles, and then when a gravitational wave goes through it, they can detect it. But there are many things in the universe that make gravitational waves that LIGO cannot see because the frequency of those waves is similar to the frequency in which the Earth vibrates, just seismic activity, and so they can't see that. So what do? And we want to see those things. Well, build LIGO in space. This is what we call LISA, another acronym, Laser Interferometer Space Antenna. So same thing, except instead of a few mile long, these laser beams are going to be a few million miles long. And it's going to be 3 different satellites shooting lasers at each other in space, measuring gravitational waves. So they'll be able to see things that even LIGO here on Earth can't see, including mergers of supermassive black holes. So these are black holes that are a few million or a few billion times the mass of the sun, and they might merge. We are not entirely sure about that. They will see these things called extreme mass ratio in spirals, where you have one less massive thing spiraling into a more massive thing in the universe. Just binaries spinning around each other, not merging or anything, that it will be able to detect. And things called eccentric binaries, which are binaries that are in weird orbits, that are like elliptical and get really close to each other and then really far. So each one of these things is also a bookmark that we have for you guys. So you can get one of these at the front, and it has explanations of each one of these things on the back side. So even if you don't actually read physical books, which And that's actually who does anymore. You can still use these. So we have a bunch of them in the backs, in the front desk, so please help yourselves to any or all of those in the series. And the reason this is in the news this month is because this mission has been planned for a long time, and finally the European Space Agency has approved the mission, and they're actually going to go forward and build this thing and launch it into space. Yes, thank you very much. And NASA is also involved. It's a joint US-European project for now. Part of the reason it was approved now is because we actually don't have the technology yet to make this happen, but they sent out one of these spaceships a few years ago, which was called the LISA Pathfinder, and just to test can we actually do this without the lasers yet, but just the other parts, and that worked like 10 times better than expected. So it was a really huge success, and following that, and following the success of LIGO, they've decided, okay, this is going to be our next big thing, is going to launch this trio of spaceships that's going to shoot laser beams at each other and measure gravitational waves and tell us a whole bunch of stuff about the universe we can't even imagine yet. So, you know, don't hold your breath, it's going to take a while. We're talking about the 2030s for this to happen, but this is how big projects happen. We don't have the technology yet, but it's approved and it's going forward, and we'll invent the technology on the way as necessary.
So what we're saying is your drunk children will be at Astronomy on Tap 2038 and watching all this, okay?
Okay, next story here.
All right, so this is a story about how gravitational lensing can magnify images of very distant things, and then we can use them to do observations we couldn't otherwise do. So we've talked about gravitational lensing many times at Astronomy on Tap. And if you'll remember, there's a cluster of galaxies here, which is a massive, whole bunch of mass, many galaxies. And then in the background, there's another galaxy. And that background galaxy is in the blue here, and it gets distorted and smeared out into this sort of ring. So that's what we're seeing here. The new thing. Stay close. All right, stay closer. All right. So the new thing here is that astronomers have managed to reconstruct what one of these smeared out, very distant galaxies looks like if you took away the gravitational lensing. So this is like if you took a funhouse mirror, and that has a very distorted wave pattern, and still doing the same thing. It has a distorted, cool, like wave shape, and if you knew that shape, you could take out those distortions and reconstruct what the person looked like originally. Right? So on the right-hand side, here's the reconstruction of that galaxy that's been smeared out. Now that galaxy, the image comes from when the universe was only 2.7 billion years old. Okay, right now the universe is 13.7 billion years old. Okay, so comes from very far away in the universe, so it's something that we otherwise could not see. So this is about, this images of the galaxies magnified 28 times. It's gotten brighter, but it's like a magnifying lens, the gravity of all of these galaxies here, but it's also about 50 times sharper than you could otherwise see a galaxy at that spot, and you can reconstruct what's going on in that galaxy and say something about it. So these little clusters, these little points of light here are clusters of stars, and each one is about 200 to 300 light years across. All right, but of course the news headlines don't exactly get that right. They say new star imagers captured by Hubble telescope with help from gravity look like fireworks. Okay, they're not star images, they're clusters of stars. So here's an artist's impression of what that would look like. It's each one is like a whole bunch of clusters of stars, and so there's these little purple and blue things where there may be thousands, many thousands of stars, tens of thousands of stars. All right, the same technology.
We should just say before you move on that our next speaker, Rachael, Dr. Rachael, is involved in this study, and this is her expertise. And so if you have any questions about that, we should ask her after the event.
It happens to be tonight. She's talking about Star Trek, but this is the kind of research that she does normally for her paid day job. All right. So next story that's very much related is weighing a white dwarf star. There are these really compact stars called white dwarfs that are about the mass of the sun but packed into the size of the Earth. And astronomers have used the fact that white dwarf stars passing in front of another star, which you can see on the left, and then that the gravity of the white dwarf star is distorting the light of the background star, and it's moving its position in space. And in fact, this was something predicted by Einstein, and it's been now used to determine the mass of the white dwarf star, and it's settled a long-standing mystery about this particular white dwarf star. And it weighed the white dwarf star. It's about 2/3 the mass of our sun. So it's the first time that a star's mass has been determined by this technique. So pretty exciting.
Okay, next story appeared on the cover of Nature, and you thought it was hot in Santa Barbara this weekend. This planet that astronomers found, it's 8,000 degrees Fahrenheit on the surface. Okay, so it's one of the hottest planets ever found, not in our solar system. It's orbiting another star. We call these exoplanets. And 8,000 degrees is hotter than most stars, actually, but this is a planet. So at 8,000 degrees, there are like no molecules can form, so not a great place to look for life, but a great place to understand the physics of planets and stars and how they're formed. Although, I'm wondering if there's like a group of people on that planet who's like, no, it's not hot, it's fine. Yeah, they're wondering if everything's okay. So this discovery, which was published in Nature, we're very happy that one of our staff members of the Astronomy, Rob Seibert, is one of the main co-authors on this paper. Rob gave a talk here at Astronomy on Tap in the past. In case you don't remember, he's the guy whose desk we showed you then. He's a pretty busy guy, and so has a pretty busy desk. But the nice thing about this discovery, other than its importance to science, is how it was made. So this planet was discovered by looking at the star, at the light from the star it orbits, and then the light dips as the planet passes in front of the star, and that's what it looks like. It's the luminosity of the star as a function of time. It dips, and this was found with a very small telescope, which images 1,000 degrees of the sky at each image, and then looks for these kinds of dips. So it images 1,000 degrees, and it's very small, so you'll know there's an acronym coming. It's called KELT, the Kilodegree Extremely Little Telescope. That is the real name of this telescope. So I was looking for a picture of it to show you, and I found this one online. And then I went to Rob and said, like, I'm looking for a picture of your telescope, not one of like when you're building it and it's still not there. I want one with the telescope. And then he said, no, that's the telescope. That little thing on the top there is a camera, and that other thing wrapped in tinfoil is a lens that they bought on eBay. This is what it looks like a little bit better. So this whole thing is like the lens about the size of a soda can. Bought on eBay, put together here, and this is one thing I love about astronomy is you can build an experiment like this, point it at the sky, discover something new, and make it to the cover of Nature, which is pretty neat.
All right, now a little something about supernova 1987A, which is the super. We'll just switch out microphones here. All right, so this is a supernova happening in a satellite galaxy to our galaxy. It's called the Large Magellanic Cloud, and it's a tiny little galaxy, but it had a supernova in 1987. It was so bright you could see it with your naked eye. Okay, so we'll zoom in, and all of these stars are in a distant galaxy. There's all these gas clouds, and we'll go into the place where the supernova exploded. This is the first supernova that you can see in more than 300 years with your naked eye. But it happened in the southern hemisphere, which is why you may not have seen it yourself. So this is the image of the supernova, and these are 3 rings of mass lost by the star before it blew up. And deep down in the center, now we're going to an artist's conception of it. Deep down in the middle, that little blob in the middle, is the actual supernova explosion. And it's helped illuminate these other rings of gas around it. So this isn't the current news article about it. These observations that this reconstruction happened were taken a few years ago. But the new thing is that there's a telescope called ALMA. We'll switch to the next one here. That's these telescopes here that are super high up in Chile that are seeing in sub-millimeters. So this is between radio and visible light that we can see. They've been able to see the 1987A in a new way. And so here's that ring of stuff that pre-existed, but deep down that blob of yellow and purple stuff are molecules that were created in the supernova. So after the supernova happened, stuff got cool, and then molecules were created. The purple is silicon monoxide, and the yellow is carbon monoxide. But this helps tell us how dust and complex molecules got formed in the universe, because that's been a big mystery. So this is one of the premier observing things on Earth, ALMA, and we've been able to tell new things that we didn't know before.
Okay. Does this just switch? Can we use this one? Is this working? Yes. Okay. I think we'll try this. Okay, next story involves a communication satellite that broke up a couple weeks ago. So this is the communication satellite before it was launched in 2003. It's pretty big. They put these things on orbits where they always stay above the same area of the Earth so that they can relay the communications in that area, so like TV channels or whatever. And so there's a bunch of these in space, in orbit, and a couple of weeks ago, the company operating this specific satellite lost communication with it. And so they asked a telescope, an observatory that has telescopes that track satellites, to take a look and see what happened. Is the thing still there? Why can't they communicate? So they took a series of images. We're going to show you here. The bright circle in the center is the satellite. There's another satellite down in the bottom left corner that is not related to the story. It's just there's many satellites in that area of the sky. And the streaky things in the background are stars. So it's kind of going to look like a scene from Star Trek where the satellite is like warp speed across the stars, and it's actually the Earth is rotating and the stars are smeared because we're following the satellite against the background of the sky. So you can see the satellite is blinking, which is not good. They're not supposed to do that. That might be a sign that it's spinning and like reflecting light off the sun at different intensities. And again, that's not supposed to happen. And if you look closely, you'll see that slowly it's becoming two satellites, which is also not the intended behavior. So yep, there are two over there. And actually, when you analyze the images a little bit closely, you can see that, yeah, there's a satellite called AMC9. There's a piece of it that flew off, and there are other pieces around it. And so since then, they were able to regain some communication, to at least turn it off so that it doesn't interfere with other satellites as it is veering off orbit. But this is actually a pretty dangerous thing, is what we call space debris, because at some point, this might crash into other satellites that then might break apart and crash into other satellites, and that'll become a chain reaction. That's a big problem. So that's why they're monitoring this very closely. They hope to regain enough communication to move the satellite up to a higher orbit where it doesn't interfere with other satellites. In the meantime, they claim there's no danger to other satellites around, but they really would need to park it somewhere safer. And also want to figure out what happened, because they don't know what caused the satellite to lose communication and break apart. However, yes.
We have obtained exclusive footage of what happened to that satellite, okay? Which we will show to you now. Alright, well, that is from Star Trek V, Kirk Encounters God, or whatever the hell the name of that movie was. Alright. Which will play into, I'm sure, Rachel's talk. Alright, next story is about hypervelocity stars. So stars that are going so fast, super velocity is not enough. They are hypervelocity, okay? So these are stars that are going about 50 times faster than a normal star. Here's an image from Gaia. In fact, this is not an image. These are actual points of stars throughout our Milky Way galaxy. And now, this started about 1 million years ago, and and we're tracing the positions of those stars from 1 million years ago to today. Okay, big secret, they didn't have a satellite 1 million years ago. We're doing this in reverse, okay? But what you can see is these little lines here are these super fast moving stars. All stars move around as they orbit the Milky Way, but some of them go super, super fast. And it's a big question, how do you get stars moving that fast? Because stars are pretty massive. They don't normally move like that. Okay, so one of the ways you might imagine this to happen is that many stars are in binary systems, and they orbit around a common center of mass. And so both of these stars are orbiting around some common center of mass. And if one star blew up, the other one would go shooting off with that velocity, that orbital velocity that it had. Or another way is that if there's a massive black hole at the center of a galaxy, as we think are in the centers of all galaxies, that could capture one star and it would send the other one shooting off. And in fact, the predominant theory of hypervelocity stars is that this is the mechanism that they come from. That they get captured, one of them gets captured by the supermassive black hole at the center of the galaxy, and the other one goes speeding off. Now, I happen to have hosted a TV show a few years ago called The Known Universe on National Geographic, and we did a bit on hypervelocity stars to try to illustrate it. Now, I did not get to write this episode or edit it, so you're gonna have to forgive me for some of the craziness in this, but we'll play a clip and try to explain our understanding of hypervelocity stars as it was.
Scenario right. We'll spin this launcher in a circle. The star that's being slowly pulled towards the black hole is a sandbag with a hole cut in it. As the bag empties, it will slowly shrink down. With nothing to hold the other star, this cannonball in place, it should shoot out like a runaway freight train.
Jake's putting the final touches on our star checker in there. Stars can zoom out really fast in a binary system when they go haywire. And it looks like our simulated stars can do the same thing. So I'm standing as far away as possible.
My plan is to stand behind Andy. He's a lot taller than I am, so I figure I'm going to be protected.
I'm going to fire this thing up, and you better duck.
So that the other one can be free. It's trapped in this bad marriage, basically. And then you gotta get rid of one partner so the other one can escape. That happens every day, both in real life and in the Milky Way.
The end of this binary star system means life for the hypervelocity star continues.
All right, so for the record, I do not condone spousal murder.
What about over-dramatic physics effects?
Yeah, well, if they didn't know it was going to come off the thing, and whatever, and that was one of our worst things, but watch the rest of the episodes of Known Universe. They're all great, okay? That was one of our worst things. But there is new information on hypervelocity stars, and that is a paper that just came out a few days ago. It says that instead of being captured by the black hole as one of the members and then shooting the other one off, in fact, many of them don't seem to come from the center of the Milky Way, and they come from satellite galaxies like the Large Magellanic Cloud that we talked about with 1987A. Those are these two little things over here to the side of our Milky Way, and it seems like many of the stars come from there. And so some of these stars are going so fast they can escape our galaxy, but other ones aren't going quite that fast, but they could escape this other galaxy. And so perhaps it's just the supernova mechanism, not this black hole mechanism that is creating them. Now, of course, as always, we show you how the media has interpreted this. So the New York Post says that the Milky Way's fastest stars are actually intruders. That's one of those headlines that sounds racist but isn't. Like maybe brown dwarfs or something, you know, it sounds a little racist but isn't. I had a half dozen of these things, but they were mostly vetoed by the other people here. But despite that, Trump has already banned them from coming into our galaxy. Okay. But actually, so I do like Uncle Straight. That's a good headline. Okay. But it is not the best headline the New York Post has had. They have the most famous headline of all time, which is Headless Body and Topless Bar. Okay. That is like, I don't know, it's just a great, great all-time headline. But this bar, you must keep your head and clothes on. Okay.
Moving on. The only reason we bring this up is because you may have seen this headline. It says, astronomers discover that our sun likely had an evil twin that killed the dinosaurs. As you can imagine, that is totally wrong. That is not true at all. So we're trying to figure out, where did this come from? Why did this write? Is this from an online thing called Futurism? I don't know if you can see it, this is from their section called Hard Science. Yeah. Okay, so what actually happened was, if you go to the press release from the actual, where they got the sources from Berkeley, where these researchers found that all stars are born in pairs. So again, they didn't actually study the sun. The only place where dinosaurs are mentioned in this press release is in the introduction of saying, like, why are we interested if stars are born in pairs? Because we think maybe the sun had a companion star, which we've searched for a while, because that could have explained what kicked, the asteroid out of its orbit that ended up killing the dinosaurs. But note that it says it has never been found. Okay. So that is the exact opposite of the title of the Futurism article. What they actually found when they look at this other place of star formation where stars are being formed, and they see that there, when you look at the process very early after the stars are formed, it looks like all of them have companions, but some of them, the companion star drifts away, and they look like then single stars like our sun looks today. It does not have a companion, but maybe it did at one time, but between that and killing the dinosaurs, there's still a lot to go. So. The other interesting thing is this was discovered by a survey which has a really great acronym. So we have to show it. It's a Van Dam survey. Stands for the VLA Nascent Disk and Multiplicity Survey. And VLA itself is an acronym, believe it or not, stands for the Very Large Array, which is the telescope they used to make this discovery. So we found this little artist conception of the discovery on YouTube.
Run for life! On fire!
And there you have it. That's our news for this month. We're going to take another short break. Thank you very much. Okay, we're ready to get started again. Our second and final presentation for the evening will be given by Rachael Livermore. So you've already heard about Rachael a little bit before. We showed some of her research. She studies these very distant galaxies that we can see only thanks to gravity magnifying them in our direction. You've also seen her skills on Jeff's t-shirt. She shows some of her other space dresses, which are pretty amazing. Yeah, so she makes these herself out of images from Hubble. And this is how she shows up at conferences. And it's the envy of everyone at the conference, as you can imagine. Rachael not only attends science conferences, she also organizes, participates, and chairs science fiction conventions. And fact about Rachel is that she has something for musicals, and she has seen The Phantom of the Opera 57 times, live and in person, and The Lord of the Rings musical 42 times. Yeah. Which is even more impressive considering that was in the span of a year. Okay. There are 52 weeks in a year, I'll just say. If you want to figure out how often she had to see that. In 2012, she drove the entire historic Route 66 from Chicago to San Francisco, and there's an excellent blog about all of the adventures that happened along the way. I recommend that a lot. But today, she's going to be telling us about the science of Star Trek, and you'll see that why she's not in a space dress today, because she's wearing something much cooler than that. So please welcome Rachel.
I had no idea they'd gone looking for those pictures. Thanks for that. But I will say about Lord of the Rings, the musical, I saw it 42 times in the space of a year, because it only ran for a year on the West End, and I was literally the only person in the world who liked it. But 21 of those were in the final month, because I was really upset that it was closing. But anyway, I'm talking tonight about Star Trek. I am obviously a science officer from the USS Enterprise, but I'm undercover here on Earth as an astronomer at the University of Texas at Austin, where I work on distant galaxies and all that jazz. That's not what I'm talking about today. I'm talking about Star Trek. So, when most people talk about the science of Star Trek, they focus on the big picture, crazy stuff, you know, warp drive, transporters. I don't care about that. Warp drive may be, in terms of physics, nonsense, but if you want to do a TV show where you're visiting a planet every week, space is really big, fine, I'll give them that. Contrary to what you may have seen on your Facebook feed today, no one has teleported anything into space. Transporters are still science fiction. So now we've got that out of the way, I'm going to get super nitpicky. You may have heard that Star Trek celebrated its 50th anniversary in September of last year. So I've done a lot of this over the last year or so, and I'm still digging out more stuff. So let's go back 50 and a little bit years to the episode Where No Man Has Gone Before. If you don't remember this, or you haven't seen it, this was actually the second pilot episode of Star Trek, the original series, but it was the first one to be made that featured Captain Kirk. So it's essentially the first episode of Star Trek as we recognize it. The premise of this episode is they find themselves on the edge of the galaxy, and they encounter this galactic barrier. So, lots of issues with this. First of all, the concept of an edge of the galaxy. I mean, the galaxy doesn't really stop, it just kind of peters away into nothingness, so defining an edge is kind of tricky. If you could define an edge, and there was a barrier there, especially a barrier that looked like this, we would have problems. Now, it's interesting that Spock says he's looking through his sensors, and he says, sensors say there's nothing there. And I'm like, really? Because, I mean, I have very limited sensors in my head that can only detect electromagnetic radiation in a very small wavelength range. And I can tell you that that is emitting electromagnetic radiation somewhere in the 600,000 to 7,000 angstrom range, i.e. purple. So they're not very good sensors, is what I'm saying. Also, if this really existed, you would never be able to see out of the Milky Way. And as an extragalactic astronomer who studies distant galaxies way outside the Milky Way, I wouldn't have a job. So, problems. So, you might be listening to this thinking, yeah, well, what do you deserve if you try looking for deep meaning in the science of Star Trek? And so people laugh when I say this is the kind of thing I pay attention to, but there's actually some really, really interesting science, not in this big picture, like main plot of the episode stuff, but hidden away in the scripts. Because Star Trek, the original series, is really, really interesting because the episodes were written by separate people usually, and generally very well-known science fiction authors. And so a lot of these people really knew their stuff, despite the evidence of the major plot arcs. And there's some really cool things hidden in there. So this same episode features this captain's log that I want you to listen to.
Stardate 1313.1. We're now approaching Delta Vega, course set for a standard orbit. This planet, completely uninhabited, is slightly smaller than Earth, desolate but rich in crystal and minerals.
So you're probably thinking, okay, what's the big deal? We just came back from a commercial break, Kirk's just filling in on what we're doing. If you're really paying attention to the science of this, you're thinking, wow, that's really cool. This planet that they're going to, Delta Vega, it's relevant to the plot that it's a mining colony, and he happens to mention that it's smaller than Earth and rich in crystal minerals. Turns out there's some planet formation physics hidden in that. The way that planets form, you start with this huge cloud of gas and dust, and it's basically homogeneous. And as it condenses, you form a gigantic clump in the center. This is what's going to turn into the star. And around the star, you have this disk of more gas and dust, and that will all fragment into little pieces. And some of those pieces will become planets, some will become asteroids, some will become comets. And all of these things clump together. They start off as gas, they become liquid, they eventually cool down and become solid. Now, if you're making planets, let's say you're making something the size of the Earth, all of the heavy elements, while it's in the liquid phase, are going to sink towards the center. This is why the Earth has an iron core. If you have a smaller planet, all these heavy elements will start sinking towards the center, but the planet will cool really, really fast. So they don't quite get there. And this is why planets that are smaller than Earth, say Mars, don't have iron cores. In fact, Mars has quite a lot of iron just kind of hovering around near the surface. That's why it looks red. It's covered in iron oxide, or what we know as rust. So if you're inventing a planet for your science fiction series that's a mining colony and you want heavy elements near the surface where your miners can reach them, making it smaller than Earth makes complete sense. So that's a really neat little bit of physics just hidden away there. But let's get to really, really fundamental physics. I want to talk about the force of gravity. So, first question, is there gravity in space? Yes, there is. This is a nerdy crowd, I'm sure you know this. If there was no gravity in space, nothing would orbit anything. So obviously there's gravity in space. What we're talking about when we talk about zero gravity, for example in spaceships, is generally you're falling towards whatever at the same rate that your ship is. So if you're in orbit, you're essentially in free fall. You're falling towards the planet, you're moving really fast, so you keep missing, so you just keep going around. But your ship is as well, so it feels like you're weightless. So on the USS Enterprise, anytime they're not accelerating, which should be most of the time if we're traveling long distances in space, you should feel weightless. Of course they don't. Any episode of Star Trek, you can see them all standing around on the bridge, almost as though they're on a soundstage on Earth in Earth normal gravity. So on their ships, they have magical gravity generators, whatever, that's fine. But one thing I thought was really cool about the most recent movie, who's seen Star Trek Beyond? Yes, some fans. It's good, I promise. I'm not given to saying positive things about the Abrams movies, but Beyond was actually okay. They did this really, really cool thing with the starbase Yorktown. Now, why there is a completely artificial starbase, I don't know, doesn't really make any sense, but whatever. For reasons, they built an artificial starbase, and they have this magical gravity generator thing on it, and because it's magical gravity, you don't have to define down in a consistent way. So on this starbase, they have these really cool situations where you have like buildings at 90 degrees to each other with down defined differently depending on where you are. And at one point, the gravity generator goes kind of kablooey, which gives you a really cool fight scene. This I thought was a really, really cool way of saying, yeah, we're in space and physics is weird, while still working within those constraints of filming your movie in Earth normal gravity. That was pretty neat. There was another really cool gravity thing in Star Trek Beyond, when you see the Enterprise at warp. This was just like a couple second clip in the movie, and it made me really, really happy. Actually, this clip is from the trailer, and when this trailer came out, I played it over and over and over again. Yay! And a normal person will not be able to figure out why. But you're not normal people, so you might notice why. This doesn't look like the Enterprise normally looks at warp. What you're seeing here is outside the warp bubble. So the way warp drive works as in quotes, is we're supposed to believe it's somehow warping space around it, folding space in on itself, making 2 points closer together than they ordinarily would be. So if you bend space, as we discussed a few times tonight, you also bend the path of light. This is gravitational lensing. And this is a real thing that we really see. This is a cluster of galaxies. The cluster of galaxies is bending space because it has mass. This is general relativity. And so galaxies that happen to lie behind it are all distorted. I know this laser focus doesn't really work, but you might be able to see like a big arcy shaped thing there. We call them arcs, because we're really good at naming stuff. These are distant galaxies where the light has been bent by the gravity of the foreground cluster. And the reason this makes me really excited is this is what I actually do. This is my day job. And so seeing it show up in a Star Trek movie was pretty cool. But there are times in the original series where I really question whether the characters understand how gravity works. So this is another little catch-up after a commercial break from Captain Kirk.
I have been somehow whisked off the bridge and placed on the surface of an asteroid, facing the captain of the alien ship.
So there are 3 reasons, just looking at this short clip, that I can tell you Kirk is not on an asteroid. All of which should be very apparent to Kirk himself. Point number 1, gravity. The amount of gravity you feel depends on how massive the object is you're standing on and how far away you are from the center. An asteroid does not have enough mass to generate gravity in the same way that the Earth does. So you would not be standing around like he is in this shot. Now, admittedly, he does pick up a boulder in a way that makes it seem like it's made of polystyrene, which is easier if you're in asteroid gravity, but walking around is a bit of a problem. Issue number 2, if you have very, very low gravity, you can't hold on to an atmosphere. This is why the moon doesn't have an atmosphere. This asteroid does have an atmosphere, so Kirk is breathing, therefore not on an asteroid. And you can also see the sky is blue. Would not be blue because it's an asteroid. Point number 3, I lied, it's not from this clip, it's from a few seconds before this clip. The super powerful alien race that put him on this asteroid actually said, we're going to put you on a planet. So, to be fair to Kirk, he was presumably distracted by this really, really weird lizard guy who was going to have to fight shortly. So, my final rant on gravity. This is my biggest pet peeve with Star Trek the original series, out of many. Anytime an original series episode needs to inject some kind of time pressure, they go for the same plot device over and over again. You get scenes like this.
Oh, we got our say. The order will stop decaying as soon as the fuel is exhausted. Say 6 minutes.
Okay, so we know how orbits work, right? I just described it as like you're falling but you keep missing. Lots of stuff orbits all the time. The Earth has been orbiting the sun for what, 4.5 billion years. It's quite happy. It's not going to stop. It doesn't have any fuel. It does not have an engine. It's just going to keep going because Newton's laws. If you're moving, you're going to keep moving unless something stops you. If you are in orbit and your orbit is going to decay as soon as your fuel runs out, you are not in orbit. That is not flying. It is falling with style. And as I said, this is a thing that keeps coming up. Here's another one.
Stop. What's our orbit status? Decaying, Captain. Variance in signal level depreciating unusually fast.
Before the Galileo was captured, whatever that phenomenon was, it drained almost all our crystals completely, including trouble.
You have a talent for understatement, Lieutenant. Without full crystal power, our orbit would begin to decay in 10 hours. We have to find it.
So, I'm kind of assuming none of these people went to the academy or paid attention in the lessons about gravity or how orbits work, which is a little bit of a problem.
We're going down, Captain. Unless we can get those beams off so we can use our engines, a duty hit atmosphere in less than 12 hours.
And this is Kirk getting know because everyone has abandoned him and he's alone on the Enterprise.
Ship can be maintained in orbit for several months with even automatic controls. I cannot pilot her alone.
So several months is better than 6 minutes. Getting there. But in the entire 79 episodes of the original series, I have only found one in which the decaying orbit makes any physical sense whatsoever. And that's the episode Tomorrow is Yesterday.
We are too low in the atmosphere to retain this orbit, Captain. Engineering reports we have sufficient impulse power to achieve escape velocity.
Give us some altitude, so guessing.
So the thing that makes this one okay is they're actually within the atmosphere. They're very, very low down. You can see clouds on the view screen. So fine, if you're low enough that you're touching the atmosphere, that atmosphere is generating friction. The friction slows you down, and as you slow down, you're going to start falling. So that one is okay. None of the others make any sense whatsoever. But on the subject of the episode Tomorrow is Yesterday, I wanted to play a quick clip from the beginning of this episode that sets up why they're suddenly in 1960s America.
Captain's log, stardate 3113.2. We were en route to Starbase 9 for resupply when a black star of high gravitational attraction began to drag us toward it. It required all warp power in reverse to pull us away from the star. But like snapping a rubber band, the breakaway sent us plunging through space, out of control, to stop here, wherever we are.
Spoiler, they're in Earth in the 1960s. So he described it as a black star of high gravitational attraction. You might be more familiar with this described as a black hole. The reason they don't call it a black hole is this episode aired in January of 1967. The term black hole was coined in 1967 by John Archibald Wheeler a little bit later than January. So if this episode had been in season 2, they might have called it a black hole. So it's going to be an excuse to talk about black holes. Black holes are cool. According to our understanding of gravity from Einstein's theory of general relativity, we know that anything that has mass curves space. So here is a really, really technical diagram of the sun, that's the yellow thing, curving space, and then we have the Earth, that's the green thing, in orbit around it. This is not to scale. So what would happen if we took the sun, same amount of mass, and we squished it into a smaller amount of space? Well, it would get denser. The amount of curvature immediately around it would get greater, but out to the same distance that the Earth was orbiting, no change. Exactly the same. The Earth will carry on orbiting. So we can squish the sun down even further to the limit of like a neutron star, the densest you can pack matter together. And again, the curvature is getting really, really steep in the immediate vicinity of this really, really dense star. But the Earth, same. It's just going to carry on orbiting exactly the same curvature it had before, because it only cares about the total mass and the distance to the center, which are the same. So we can squish this even more, and at this point, we get this creepy singularity, which is what defines a black hole. And at this point, at that singularity, the curvature is theoretically infinite. I no one really understands what that means in physical terms, hence hole. But what this means, as far as the Earth is concerned, it suddenly got really dark and really cold, because you can't see the black hole, you can't feel any heat or light from it. But in terms of its orbit, no change. It's just going to carry on orbiting exactly as it was before. So the moral of the story is black holes do not suck. If you are in orbit at a safe distance, you will stay in orbit. You can orbit a black hole totally fine. What you cannot do is go past this event horizon. This is the point where your escape velocity, this is how fast you have to be going to escape the gravity, exceeds the speed of light. Now in our universe, nothing can go faster than light, hence nothing can escape a black hole, not even Matthew McConaughey. But in the Star Trek universe, they have warp drive, they can go faster than light. Hence, they were able to escape this black star using full warp power in reverse. We see this again in Star Trek 2009, where they're able to escape a black hole using full warp power. And Kirk says something like, why aren't we at warp? And Scotty says, we are, because they are actually traveling faster than light, and they're only just able to break away from this black hole. Now, I actually have many, many rants about this scene, which you can catch on YouTube and I'll give you later. But this brings me into stuff that is wrong just because they didn't know it in the 60s, like the term black hole. And a really cool example is from the episode Galileo 7, where we learn that the Enterprise has standing orders to investigate all quasars and quasar-related phenomena. And this is the image you see in the original version of the episode of a quasar. Now, quasars were really mysterious in the 1960s because they're incredibly bright, and they kind of looked like stars, but they looked like stars as though they were really far away, but they couldn't possibly be really far away because then they would have to be absurdly bright. So no one really understood what they were, hence the Enterprise having standing orders to investigate them, I guess. Now, since the 1960s, we figured out what these things are. They're actually black holes that are accreting stuff very, very fast. Now, although you can't see a black hole, all this curvature in space causes stuff to move very, very fast. And you can see stuff that's moving very fast because it has a lot of energy. So when they brought out the remastered edition of this episode, they updated this image. This is more what a quasar looks like. So you can kind of see there's an accretion disk in the middle, a black hole being at the center, you've got all these jets coming out. So this is great, but two problems. First of all, one of the things we discovered is quasars actually really are very, very far away as in way, way, way outside of our galaxy, and they really, really are that bright. Problem number two is he updated the image, but the dialogue is still the same. So Kirk looks at this quasar, now the image on the right, and says this is a faint, fuzzy, nebulous blob, and you're like, really? So I'm not really sure why they updated it. Several things that were just not really known in the 60s that we have more of a handle on now are numbers of stuff in the universe, which gives me an excuse to show one of my favourite scenes from the original series. This is McCoy talking to Kirk in the episode Balance of Terror.
In this galaxy, there's a mathematical probability of 3 million Earth-type planets. And in all of the universe, 3 million galaxies like this. And in all of that, and perhaps more, only one of each of us.
So the reason I really like this scene is an awful lot of science fiction does this whole space is really big and you're really small thing because the size of space is kind of mind-boggling. And usually the punchline is, so you're really insignificant and nothing you do matters. And I like that this one kind of does the opposite. It says that because in all of this there is only one of you, what you do really does matter. And I think that's really cool, but because there are numbers in it, obviously I'm going to pick it to pieces. So first of all, we hear McCoy say that there are 3 million Earth-type planets, and he's just talking about in the Milky Way at the moment. So this was completely unknown in the 1960s. It was even completely unknown when I was an undergraduate, which was more recent than the 1960s. But we have a better handle on it now, thanks mainly to the Kepler Space Telescope, which launched in 2009 and has collected most of what we know about populations of exoplanets. And what we think we know is that about 1 in 5 stars similar to the Sun probably has an Earth-type habitable planet. So there are around 20 billion with a B, stars like the Sun in our galaxy. So that gives us around 4 billion Earth-type planets. So this is an order of magnitude, several orders of magnitude, more than McCoy thought. And this is just around Sun-like stars. Most stars are a bit smaller than the Sun. They can have habitable planets too. So this is actually a lower limit, and it is way, way, way more than McCoy thought, which is pretty cool. He then goes on to say 3 million galaxies, which is a weird way to express that number. It's around 3 billion, I guess. Trillion? 3 trillion. So billion is defined differently in England and the US, and I always forget which one is which. So 3 million galaxies, how many galaxies are there? Our best information about this comes from the Hubble Ultra Deep Field, which is the deepest image ever taken by mankind with the Hubble Space Telescope. And this is a tiny image. If you take a penny and you hold it out at arm's length, Lincoln's eye would completely cover this image of the sky. And yet, in this tiny, tiny little speck, there are around 10,000 galaxies. So you assume this is a fairly average bit of space, you extrapolate over the whole sky, you get there's probably around 1 trillion galaxies. So actually the point was pretty right, which means that my entire field of research has really achieved nothing since 1967. So that's great. Don't tell funding agencies that. He then finishes with only one of each of us, which might sound like a given, but this is Star Trek. So, in a quick count, we have transporter accidents, we have androids, we have alternate universes, the Mirrorverse, and now, of course, the Kelvin timeline. We have shapeshifters. So, actually, I'm going to call that plane question. Now, very, very quickly, a weird thing that Star Trek has a massive problem with for some reason is nebulae, which I'm bringing up purely so I can show a clip from the Rock of Khan.
Why are we smaller? Can't follow them into the nebula, sir. Shields would be useless.
So this is the scene where they're heading into the Matara Nebula, and they're saying none of their shields are going to work, and so they can't possibly be followed in there, right? And this is a thing that comes up again in Star Trek Beyond just last year.
Our mission is straightforward. Rescue a crew stranded on a planet in uncharted space. Our trajectory will take us through an unstable nebula, one which will disable all communication with Starfleet.
So are nebulae really this scary? Here's an image of a nebula. It's a region of space that contains a lot of gas and dust and is where new stars are forming. Notice the distinct lack of lightning. I don't know where that came from. So it looks like it's pretty dense, and so you might imagine this would disrupt your communications, right? So there is no such thing as a vacuum, really, in space. When we talk about the vacuum of deep space, we mean that there's about 1 atom per cubic centimeter or so. And if you go into a nebula, it's more like 100,000 atoms per cubic centimeter. So you're like, okay, that's really dense, right? But actually, we've seen the Enterprise operate in situations that are a quadrillion, that's one with 15 zeros, times more dense than a nebula, and that is air. So, nebulae, really, really not that scary. Don't we understand? If the Enterprise can't work in a nebula, they need a bit of an upgrade, I think. So a thing that science fiction always, always, always gets wrong is any kind of action or explosion. How many things were wrong in that tiny, tiny clip? So the main one I want to point out is the obvious one, sound in space. As I said, space is not a vacuum, but the particles are too spaced out to transmit sound, so you wouldn't actually hear any of those explosions. And the excuse everyone gives for why you have to have sound and explosions in space movies is drama, right? And so, as a counterpoint to that, I have another scene from that same movie. So this is all noise, explosion, panic, until she gets whisked out into the vacuum of space and then silence, and tell me that wasn't dramatic. Like, you can totally do drama and obey the laws of physics. Now, obviously, I'm being super nitpicky, and none of these things are the point of Star Trek. And just to hang a lantern on myself and how ridiculous it is to care this much about these tiny details, I want to finish with this scene from Star Trek 2009, in which Spock has to watch the destruction of his own planet. That's a spoiler, sorry. This movie came out 8 years ago. So where is he watching this from? It's a place called Delta Vega. If you have a really good memory, you might remember that I've already mentioned Delta Vega once in this talk. This was this mining colony, but this was on the edge of the galaxy, so this is definitely not that Delta Vega. It looks like it might be a moon of Vulcan, because it's really close. You can see Vulcan on the sky, kind of resolved, except
Vulcan has no moon.
so it's not a moon, or is sitting on Vulcan, and in the background you can definitely see that is a moon, really, really big one. And if you watch Star Trek the Motion Picture, which I'm not suggesting is a good way to spend your time, but if you do, you will also notice this is Vulcan, and look, there's like gigantic, like possibly another planet and moons and all sorts going on. Unless you watch the director's cut, again, not recommended, but if you do, all the moons have vanished. Because I guess the director knew Vulcan has no moon. My point is, I am fully aware that looking for consistency in Star Trek is a futile exercise, but it's fun, and it gives you an excuse to talk about aspects of science you don't normally think about, which is great. The main point of Star Trek, of course, is not the science, it's a setting for truths about humanity. And this is best summed up in my favourite Star Trek quote. This is from the original series episode, The Corbomite Maneuver, when Kirk says, "You know the greatest danger facing us is ourselves, an irrational fear of the unknown. But there's no such thing as the unknown, only things temporarily hidden, temporarily not understood." Very relevant in the 1960s, and as evidenced by the fact that it was quoted again in Star Trek Beyond, equally relevant, I think, today. And this is the real point of Star Trek. It's an optimistic view of humanity and what we could become if we could put aside our irrational fear of the unknown. So I will leave it there. I just want to let you know that if you enjoy nitpicking as much as I do, you can find me on Tumblr as Snarky Astronomer. I started rewatching the original series for the 50th anniversary. I've finished season 1, I'm about to start season 2, and I nitpick in excruciating detail. Also, Astronomy on Tap ATX, Austin, Texas. It's where you can find videos of some of my other talks, including my talk on my actual research, gravitational lensing, which I've already given tonight, but I heard you've already had one, so I get to talk about Star Trek, so that's great. And also full 20 to 30 minute rants about individual movies that I've mentioned tonight. And I have one coming up, Star Trek The Wrath of Khan. I host a series of movie screenings at the Alamo Drafthouse Movie Theatre in Austin. We're doing Star Trek The Wrath of Khan on July 27th. We show the movie and then I rant about the science for half an hour. It's great fun for me. If you happen to be in Austin, there's still a few tickets available. If not, all of these go up on YouTube shortly afterwards. So, thank you very much.
We will take a few minutes while we gather questions for
Yes.
Rachael.
Thank you for those who have sent them during the talk. They're excellent. Please keep them coming. Send them now because we're not going to have another break. We're just going to send your questions now while Andy tells you about our upcoming event.
All right. So the distance from the microphone and whatnot. So one upcoming event we're having is, it went away. Anyway, Tim Brown was talking about the spinning sun and other binary systems and so on. So he will be talking at the Center Stage Theater, and it is a free talk that will be happening on Wednesday, August 9th, here we go, at 7 p.m. And so please come out for that if you can. I think in the meantime, while Yair is trying to figure out questions, Rachel's talk brought up a whole lot of beefs I have with her over some science and Star Trek stuff. You might remember I gave the science of Star Wars, the superior here. But I have my own strong feelings about Star Trek, and how can you diss Star Trek the Motion Picture directed by Robert Wise, who also directed West Side Story, The Sound of Music, and so on? I want to hear your defense of it.
Yeah, you can't attack me when I don't have a microphone. That's not fair. Okay, I am a huge Star Trek fan. I like the motion picture because the actual plot of it is about the relationship between Kirk and Spock. but it is an objectively terrible movie. The pacing is appalling.
5-minute shot.
Okay, I think we're going to switch the questions.
No, please.
This could go on for a while.
Later, you can gather around and we'll be arguing about Star Trek. Because we have a long-standing thing over whether or not Star Trek 3 is a piece of shit or not.
Yeah, I don't care how tall you are, I will fight you. No, Star Trek 3 is the best Star Trek movie, hands down.
Oh no. Okay, questions. Give her the microphone. Okay, so I'm just going to preface this question with, you started the asteroid thing. Why could the asteroid that Kirk walked on not be extremely dense? Would that be able to give it enough gravity?
Oh my god. I can't do the math in my head, but for the asteroid to have enough gravity to walk around on as if it was Earth, we're probably talking like black hole density, right?
I can't do math in my head either, but I think we're close, yeah.
Sure.
Okay, what is the nearest class N planet?
There you go, that was mine.
Yes. Well, we should explain what is meant by that.
So in the Star Trek universe, a class M planet is loosely defined as habitable, which means it looks weirdly like Southern California. So Earth gravity, nitrogen, oxygen, atmosphere. The closest class M planet that I could 100% guarantee exists is the one we're standing on right now. There's possibly, maybe, one around Proxima Centauri. Maybe. But I'm not going to stake my life on that.
That was my question. Terraform.
Terraform or terraformable?
There you go. Terraform.
I mean, I don't know. Define terraformable. Mars, the problem with Mars is it doesn't have a magnetic field, which is why it doesn't have much of an atmosphere. It got stripped away by radiation from the sun, which gets very nicely deflected on Earth by the magnetic field.
What about Europa?
So, I mean, we couldn't live on Europa, but that's not to say that other forms of life can't and maybe do. So yeah, if you're defining class M as habitable to humans, I personally would not choose to live anywhere in the solar system other than Earth.
But if you had Alright, this is why we have people submit questions via text message. Alright, so there.
There are a few other good ones. Someone says in a season 2 episode of DS9, a scientist completes his life's work by reigniting a star. Is that possible?
Yes,
So who's seen the movie Sunshine? Documentary, right? Reigniting a star? I mean, we have never successfully made a sustainable fusion reaction on Earth. So I'm not really sure how you go about doing that in a star. If for some reason it's switched off, which presumably means it doesn't have a sufficient density of hydrogen.
I was saying.
Yeah.
Yeah, the thing that ignites stars is their mass. So just add stuff to it, and maybe they'll eventually ignite.
So I actually have a theory that this is what red matter does in the first Abrams movie. It's actually adding matter to things. So there you go. Red matter is how you ignite a star.
Okay. Has anything in science fiction motivated your hard science interests or research?
I mean, the fact that I'm an astronomer is entirely because I grew up reading science fiction. I used to read more books than my mum could afford to buy, and so she would just go to charity shops, and I don't think we really have those, but like Goodwill, but for small charities, and just raid whatever book she could find. And one day she happened to pick up a book of Isaac Asimov short stories, and I was like, what is this, and where can I get more? And years later, I'm a scientist, so yeah.
Okay. One last question. I don't know what I'm stepping into here, but we're going to try this. What is the most scientifically accurate sci-fi movie or TV show?
So, One of the purposes of the movie series that I host at the Alamo Draft House is to try and find the most scientifically accurate movie. But I actually think Andy has the best quote about this. When asked what the most scientifically accurate movie was, he just said what any rom-com said on Earth. And yeah, that's scientifically accurate. The gravity kind of works, but boring. So the most scientifically accurate movie where they actually attempt to do stuff with science is probably a better phrasing of the question, a better interpretation of the question. I don't know, I did Apollo 13 week before last, and that was kind of cool, except that I found out that Tom Hanks can't do math. If he freeze frame on his arithmetic, it's wrong. That's the kind of thing I do. I actually really liked Gravity, despite several massive flaws. And The Martian, I thought was really well done. I really hated Interstellar with a passion.
Yes.
And again, I like fight people over that.
Okay, I think we're going to end on that note before it gets out of control.
You guys agree on that?
Yes. Let's see here. I need your pen, your clicker. Our last order of business for today.
All right, now is the time when we do drawing of the raffle tickets, so you can gain awesome beer glasses that I drink out of every day. So every day, I remind you of astronomy on tap. Wait, did I just say I drink every day? That's very little. So, while Jair is coming up with some graphics, which really don't matter about our raffle.
Oh, hang on.
Come up with some actual fishbowl of raffle
There we go.
tickets.
Okay, let's get. Okay, everyone get your raffle ticket, your side of the raffle ticket that you have received on the entrance. It has a number on it. We're going to raffle the other side of the ticket, and if we call your number, please come up stage and get your beer glass. These beer glasses are one of a kind. They have the Astronomy on Tap logo on them, so you cannot get these anywhere other than here. So if we call your number, please come up and get it, or we'll give it to someone else. And we'd like Jeff to come up here and also help us pick numbers. Okay, Andy, you start with me.
Yeah, all right, we'll start with me because I'm right next to the fishbowl, and it is 039710.
710, are you here? Make some kind of noise and come down, or we're going to give your glass away. Doesn't sound like it.
Some kind of losers that left early. There's nothing else to do on a Wednesday night in Santa Barbara, trust me. That's why we set this on Wednesday night. All right, 742.
Okay, number ending in 742. Are you here? It doesn't look like it, so we're going to move on.
Yeah, a bunch of losers. All right. 039817.
Okay, let's keep going.
Man! Wow. All right.
Come on.
Yeah. 039839. Somebody got close. Not quite though.
Somebody text you our number.
Faster, yeah.
Yeah, exactly. All right. How about number 818? Ending in 818.
Come on. Where are you? We have 4 of these glasses to give away.
Yeah, 874.
874 is here. Okay. Let's have the mic and go over to Jeff here. Hopefully you do a better job.
It's on. Oh, it's on. It's on. All right, we got 780.
It's not
You?
over to
All right. 780.
Yes,
Last
last
three
number is
numbers.
780.
Yes, 780.
Are you here? Yes, come on. 716. See, Andy, that's how it's done.
780.
Awesome. I won a. All right.
Okay, last one.
Thank you.
I'm going to do the last one here. Okay. You better be here. 039807. 807. No, it does not sound like it.
They hate the locals here.
039725. Yes. Okay. Well done. Congratulations.
Thank you.
Thanks. Okay. We would like to remind you, we don't know when our next Astronomy on Tap is going to be, but we hope it will be in a couple of months if we can get some funding to continue. And if you enjoy Astronomy on Tap, please help us find our funding savior. And in the meantime, we'd like to thank our two fabulous speakers from today. And also thank Andy.
And Yair for figuring out how to do this whole thing.
Thank you very much. We'd like to thank the Lucas for hosting us and everyone who works really hard to make Astronomy on Tap happen. And we hope to see you all soon in our next event. Thank you very much.